The universe stops rendering when you stop looking. It's not a metaphor. The stars stutter. For a heartbeat, Orion flickers like a buffering video, then steadies. You hold your breath. Was it you or the sky? Here's the thing. What if reality doesn't load all at once everywhere, but only where and when it's needed? Locally. Efficiently. Tonight we're testing a sharp idea with real stakes. The universe might render just enough to keep your story consistent. The boundary that matters isn't a wall of brick, but a limit of information. The cosmic horizon, the farthest map tiles loaded in your instance. From quantum labs to the edge of the sky, we'll ask, what changes when we look away? The map that ends, what the cosmic horizon really is. To understand where the map ends, we need to separate two edges people often mash together. There's the particle horizon and there's the event horizon. They sound similar. They aren't. The particle horizon is the farthest light that could have reached us since the Big Bang. Today, that sphere is about 46.5 billion light-years in comoving distance. Wait, 46.5, not 13.8. Here, the trick. The universe expands while light travels. So a photon that left a nursery galaxy when the universe was young has been flying through space that's stretching under it. The path length today isn't the light's travel time. It's the current spacing of the markers along the way. That's why you get a larger number. The map doesn't have an edge like a cliff. It has a limit set by time and expansion. Now the event horizon is colder. Stand in our patch and ask, what events anywhere can ever send me a signal if I wait forever? Dark energy pushes the answer inward. In a universe where expansion accelerates, there's a boundary beyond which even light aimed our way now will never reach us. That's the event horizon. It's not a wall. It's a promise that some stories will never cross into our lives. Here's where it bends your brain. Galaxies beyond a certain distance recede from us faster than light. That doesn't break relativity. Space itself expands. The speed limit binds motion through space, not the growth of space. So you get a universe where recessional speed can exceed c and signals still obey the rules. Your local light cone, the set of events you can affect or be affected by, sits inside this larger stretching fabric. Horizons are the geometry of causality, drawn by expansion and measured against what light can actually cross. What nobody told you when you first saw those Hubble Deep Field posters is this: the edge of the visible universe isn't a painted dome. It's a time limit. Light takes time, expansion adds distance, and we sample a shell of histories. We don't see the universe as it is now. We see many nows, stacked by distance, with the farthest nows older than galaxies themselves. So why call it a map that ends? Because beyond the particle horizon, no light has had time to arrive. Beyond the event horizon, no future light will. That's causal disconnection. If you're thinking in render terms, that's an unloaded region, not because a programmer forgot to fill it in, but because no message can request it. No ping, no texture. If no signal can go there or come back, then for us, it's out of scope. Meanwhile, the shoreline moves. Yesterday's particle horizon is smaller than today's because light keeps arriving from just beyond our previous limit. We're watching an ocean tide of information roll in, one faint photon at a time. Survey teams plan like cartographers at a shifting beach. New instruments, deeper exposures, careful calibration, always pushing the fade where noise overtakes signal. They're not drawing continents, they're catching whispers. Here's a micro story. A grad student schedules telescope time to map a patch near the South Galactic Cap, empty enough to cut foreground dust, rich enough to catch high redshift galaxies. She triple-checks the guide stars, then watches the first frames come in. Cosmic rays pepper the CCD. Distant smudges float in. She doesn't know it yet, but one of those smudges sits a little closer to the particle horizon than anything in last year's catalog. It's not a new edge. It's just the next grain of sand added to our shoreline. Let's talk distances because words can trick you. Proper distance now means how far that galaxy would be from us if you froze expansion at this instant and measured with a cosmic ruler. Comoving distance scales with the expansion. It keeps markers fixed relative to the flow. Light travel time is just the number of years the photon has been flying. Those aren't the same numbers. When people say the observable universe is 93 billion light-years across, they mean a diameter in moving coordinates, not a simple outand back of light-years as time. The map's units depend on which grid you pick. And no, there isn't a sharp boundary in the sky. There's no place where galaxies turn into static. What happens is flux drops, wavelengths stretch, sources redden and dim, and eventually even our best detectors can't dig signals from the noise. That instrumental edge sits inside the physical particle horizon and moves as we upgrade our gear. The physical limit sits beyond that, and it moves too, because the universe keeps aging. Here's the heart of the matter. We want to treat the cosmic horizon like a fence around a yard, but it behaves more like a bandwidth budget. Within our horizon, interactions are possible. Information can circulate, structures can form and talk to each other slowly, bounded by light. Outside for us is unaddressable, not fake, not absent, just permanently offline to our instance. If you're holding the simulation metaphor, fine. The world renders where causal contact can, in principle, ask for it. No contact, no load. And yet, while the big map stretches and the shoreline creeps, the small game plays by other rules. Down in the lab, reality sometimes looks like it's deciding what to be only when someone checks. That tension, cosmic smoothness versus quantum choice, sets up the next move. We've drawn the border of our map. Now we're going to look at who, or what, decides what fills it. The observer problem, quantum choices and collapsing possibilities. Down in the lab, the universe refuses to play classical. A beam of electrons hits a plate with two slits. On the screen behind it, you don't get two bright bars. You get an interference pattern, dark, like ripples crossing. Waves, so far, so good. But now you add a tiny detector at the slits to ask a simple question. Which path did each electron take? The interference disappears. The screen shows two bars. The act of extracting path information rewrites what lands. Here's where people leap to consciousness collapses the wave. Slow down. The experiment doesn't care who's watching. It cares whether which path information exists in principle. If the environment, air molecules, photons, a micrometer, leaks that information, the interference fades. That's decoherence. The world is full of observers, and most of them aren't conscious. They're stray fields, vibrating lattices, warm instruments. They snatch fragile quantum superpositions and push them into stable, classical-looking states. But what do we mean by collapse? Depends who you ask. In Copenhagen-like views, the wave function is a tool for predicting outcomes. When a measurement happens, you update the tool to match the result. No deeper mechanism offered, don't ask, just calculate. In many worlds, nothing collapses. The wave function evolves smoothly, and measurement entangles you and the apparatus with the system. You end up in branches where each outcome is realized. The interference vanishes locally because you can't talk across branches. In cubism, the wave function is personal. It encodes your expectations. Observation updates belief. These aren't idle labels. They shape what you think rendering even means. Let's keep this concrete. Decoherence says the environment singles out preferred states, pointer states, that survive the noise. Position of a dust grain, orientation of a pointer, current in a superconducting loop. The timescales are brutal. A micron-sized dust particle in air decoheres in about 1031 seconds for position superpositions larger than a wavelength of light. That's functionally instant. Macroscopic stuff stays classical because the universe won't stop measuring it. This is the plant from earlier. Selection isn't rare, it's relentless. So does the lab prove the universe renders only on demand? Not exactly. The lab shows that acquiring information kills certain interferences. It shows that outcomes appear definite because branches stop talking. It shows that being looked at, in physics terms, is just interacting with enough degrees of freedom to make history separate. Consciousness doesn't enter the equations. Entanglement does. If you hold the rendering metaphor, swap observation with information flow. The world renders. when information about alternatives becomes locally available and effectively irreversible, when erasing it would cost energy and leave detectable heat. Here's a micro story. A student aligns a delayed choice experiment. Photons pass the slits, then later, a choice is made to erase or preserve which path information. The pattern on the screen depends on that late decision. No signal goes backward in time. What changes is whether histories are recombined or kept separated. The student stares at the plots and whispers. It's like the past waits for the question we're able to ask. The advisor nods. It waits for the context. Now bridge up a scale. Can the same logic shape galaxies? You're not measuring a star with a lab detector, but the star is bathed in photons, gas, magnetic fields, gravity. It's coupled to a background of microwave photons, to dust, to neighbors. The cosmos is a giant environment. Decoherence at cosmological scales says the expanding background selects stable classical variables, density contrasts, curvature perturbations, out of primordial quantum fluctuations. That's selection on a sky-sized stage. What looks like rendering is the universe locking in choices through interaction, not waiting for eyes. Still, there's a sharp stake here. Is observation special? If you demand a conscious mind, you've left physics and entered metaphysics. Every successful quantum device we've built works without minds at the point of interaction. A photodiode flips. A superconducting qubit dumps a photon into a cavity. A cosmic ray hits silicon. Information moves, interference dies. If information transfer is enough, then the rule is cheap. No magic, just entanglement growth and entropy bookkeeping. But there's a cost. Landor will show up later with an energy bill for erasing information. For now, notice the pattern. The universe avoids keeping track of the impossible. You can't build an interference pattern if which path leaks. You can't signal outside your light cone. You can't see beyond your horizon. The same theme repeats, selection by constraints. Here, where it nudges our metaphor. If outcomes get fixed where and when interactions spread information, then rendering is local and context-dependent. Not a central server deciding frames, but a network that stabilizes facts when enough links form. And because decoherence times are brutally fast for big things, your everyday world looks crisp by default. The mystery isn't why it's classical. It's how anything stays quantum long enough to matter. Hold that frame. The lab taught us that selection burns possibilities into facts when information escapes. Next, we'll ask how the cosmos might be running an efficiency play, minimizing what it keeps explicit, compressing what can be inferred, and budgeting the cost of information itself. Efficiency as a law, cosmic minimalism, and the energy ledger. If observation is information flow, then there's a price list taped to the back of reality. The universe is thrifty. It spends only when it must, and it compresses whenever it can get away with it. Start with entropy and the way we actually describe systems. We don't track every molecule in a room. We use temperature and pressure. That's coarse graining, keeping the variables that matter for outcomes, discarding the microscopic clutter. And here's the kicker. The macroscopic laws we trust, like thermodynamics, emerge because so many microstates map to the same macrostate. Efficient descriptions win because the world doesn't need the rest for predictions at our scale. Now bring in Landor's principle, the bookkeeper's favorite line. Erasing one bit of information costs at least kT ln2 of energy dissipated as heat. It's not a metaphor, it's a measured bound. A memory reset in a computer dumps heat. A demon trying to cheat the second law pays his tab at the eraser. Translate that. Information isn't free. Losing track on purpose, resetting, compressing, overwriting, has an energy toll. Any rendering scheme that creates, stores, or clears bits is pinned to physics. What about the universe itself? There's an eerie hint in the holographic principle. Black hole thermodynamics tells us the entropy, the number of possible internal configurations, scales with the area of the horizon, not the volume inside. 1/4 of the area in Planck units gives you the bit count. That's so strange it sounds like a parable. The boundary knows more than the bulk. In lab-grade theory, add SCFT makes that literal. A gravitational world in the volume is exactly encoded by a quantum theory on the boundary. Our universe isn't de Sitter, so we can't copy-paste, but the pattern is loud. Count bits on surfaces, not in volumes. If bits scale as area, full resolution everywhere becomes absurdly expensive. You don't store every voxel's microstate in explicit detail. You keep boundary data and let bulk behavior be an emergent, efficient consequence. That's compression. Not sloppy, not lossy in the predictive sense, but minimal. The state you need is only as detailed as the questions you can physically ask. Here's an analogy with teeth. In software, lazy loading fetches assets when a player walks into a region. In physics, sparsity and symmetries cut the cost. Fields are smooth over scales, interactions have ranges, correlations fall off with distance, gauge redundancies hide wasted description. You never paid for every pixel. You paid for modes that carried energy and information across your horizon. Everything else stayed on the shelf as potential, not instantiated bookkeeping. Bring back Landor and ask about the ledger at cosmic scale. Every time information is irreversibly recorded, when decoherence spreads and alternatives can't re-interfere, you've effectively allocated bits to classical history. You can't unspend that without a matching energy cost. Erasing is heat, storing is entropy. The universe chooses to let most details wash out, keeping only robust, redundant records, multiple photons bouncing off a chair, many molecules carrying the same trace. Redundancy sounds wasteful, but it's how facts become objective. Many witnesses, same story. Now stack this with the horizon. If the maximum number of bits inside your patch scales with its boundary area, then there's a hard ceiling on how much distinct detail can be physically present and retrievable within your worldline. You're living in an instance with a storage budget written on its edge. Try to imagine full fidelity everywhere, all at once, and you run straight into the bound. There's another efficiency play hiding in entropy and coarse graining, effective theories. You don't simulate quarks to model airflow over a wing. You use Navier-Stokes within a domain of validity. The cosmos does the same. Long wavelength modes govern structure growth. Short wavelength noise averages out. Inflation stretched quantum jitters to cosmological scales, but even then, only specific combinations survived to the microwave sky. The rest got smoothed, packed into parameters, compressed into a handful of numbers. Spectral index, amplitude, baryon density. Minimal inputs, maximal reach. Here's a micro story. A team running a galaxy formation simulation fights memory limits. They can't resolve every star, so they build subgrid models, rules that stand in for unresolved physics. Feedback from supernovae isn't simulated per blast. It's injected as heat and momentum according to calibrated laws. Critics grumble. Then the results match observations better than brute force versions did. The lesson lands. The right compression preserves what matters. But there's a cost to every shortcut, and physics forces honesty. Landor says you pay to forget. Holography says you store on the edge. Thermodynamics says high-entropy states are typical, so order must be local, engineered by gradients and flows.